Hello, students. Welcome back to Tuition Masters. And today we are going to do a one shot theory session on the chapter Structure of Atom. So let's understand what all things are we going to cover. So we are going to understand about the discovery of subatomic particles, Thomson's, Rutherford's and Bohr's atomic models, shells, valency, atomic number and atomic mass, as well as isotopes and isobars. So let's get started. Now our first topic is the discovery of subatomic particles. Now in the last lecture we had in the last chapter we had understood about Dalton's atomic theory. Dalton gave a postulate that the atoms are indivisible, means we cannot divide atoms further, but it was proved wrong through various experiments which we are going to study ahead, and it was proved and shown that atoms also have three subatomic particles in them, which are electrons, which are the negatively charged particles, which are even represented by E minus. Next, protons, the positively charged particles also named as P plus, and neutrons, which are the neutral particles. So even under atoms, as Dalton said, it was indivisible, but under atoms also we found electrons, protons and neutrons. Now, let's understand the discoveries. So, basically, electrons were found by J.J. Thomson by this cathode ray experiment. Electrons he found out. Entire detailed thing you will understand that in grade 11. So, right now it's not required. So, electrons it was found by J.J. Thomson by the cathode ray experiment. Now, in using those cathode rays only, protons were formed by Eugene Goldstein, even known as E. Goldstein, by the canal ray experiment. Here is the diagram. And the neutrons were found by James Chadwick. What did he do? He bombarded beryllium with alpha particles. Here, if you see, like from alpha source, alpha particles he radiated, then protons were found, then beryllium he bombarded, so neutrons were found. So, here was the discovery of electrons, protons, and neutrons. Now, our next thing is the three models: Thomson's, Rutherford's, and Bohr's atomic model. So let's understand Thomson's atomic model. So Thomson's atomic model basically it he represented this like a Christmas pudding model also, like this was a Christmas pudding. Now what did he say, that this entire sphere kind of pudding, he said that this is the positively charged sphere, okay, and inside that are these currents or plums which we can see. He named that these are the negatively charged particles, which are nothing but the electrons. So here is how he explained how like the atom look like, and in real this is how he explained the model. Like there is a sphere, okay, which is positive, which has a positive charge, and inside them these are the electrons. So this is how he explained it, and this model of his was also known as the plum pudding model because it looked similar to that. Now, what were the postulates he gave? He gave that an atom it has a consists of positively charged sphere and electrons, which are the negatively charged particles embedded in it. Means inside it, as we can see in this model, and even here also. So, the sphere entirely is positive, and inside that the negative charges are embedded. And secondly, he also gave that the negative and positive charges are equal in magnitude. If I have negative, I have positive, so what will happen? It will become zero or neutral. So he said that atom whole is electrically neutral only. He said that it is neutral only. Only positive and negative charges are there. They are equal in magnitude, so it is neutral. But there was a demerit also. It was that other scientists couldn't explain that atom is neutral by this model. The model with the scientists say, okay, you are saying that it is neutral, okay, fine. But when they took his model and tried to find out, no other scientist could explain that this is a neutral, atom is neutral. So this Thomson's atomic model was also a failure. Next came Rutherford's atomic model. So, Rutherford's atomic model was also known as the gold foil experiment. It was basically the gold foil experiment through which he discovered the different things. So like this was how his experiment looked like. This was a gold foil he took, then there was the detector on which the different strikes were there. This was a radioactive source from the light, and these were the particles which came from the radioactive source. So what did he observe is that the fast moving alpha particles, okay, this is the sign of alpha particles. The fast moving alpha particles, they pass through the gold foil. The alpha particles which are there, like here, if you see here on there is yellow, so those are the alpha particles. Directly they went through the gold foil. He even observed that some of the alpha particles were deflected by the foil by minute acute angles, like small angles. They were diffused also. Even one surprising outcome was that every 12,000 particles appeared to rebound. Like out of 12,000 particles, one out of every 12,000 particles appeared like they are rebounding. So these were his observations with this gold foil experiment. Now, Rutherford gave some postulates also, that there is a positively charged center in an atom which is called the nucleus. So basically, this was his atomic model, Rutherford's atomic model. So he said that in the middle of the atom, there is a nucleus which is positively charged, and nearly all the mass of the atom, whatever the mass is, almost more than half of the mass of the atom stays in this nucleus only. The nucleus has it. Second postulate he gave, that electrons, the negative charged particles, they revolve around the nucleus in circular paths, and these circular paths were known as orbits. These are known as orbits. So he said that these electrons which are there, these revolve around like this, they will move like this, they will move like this, they will move like this, they will be moving. And even he said that the size of nucleus is very small as compared to the size of atom, in that the nucleus is very small when we compare it to the size of atom. So these were his postulates. But again, demerits also. Atoms are quite stable. Okay, we know right now that atoms are very stable. But in this is thing, that when the electrons are moving in their orbit, when they do the revolution, so what will happen? Acceleration will be there. Acceleration would result what? Due to extra acceleration, the electrons or any other particle would fall in the nucleus, and the atoms will be unstable. But these all things weren't included in his model, so this was also failure. Then came the model which was universally accepted, which was the Bohr's atomic model. Now, in Bohr's atomic model, he explained it in this way, that there are some shells out, in the atoms. So, how he explained? Let's understand his postulates. Now, he said that only certain special orbits are known as discrete orbits of electrons, and they are allowed inside the atoms. So some now in there are some orbits here, okay, which we are going to study in detail about them. So they are known as discrete orbits, not all. Only some orbits which have special properties are known as discrete orbits of the electron, because electrons are going to move in those orbits. And while revolving, when electrons will revolve in the discrete orbits, they will never radiate energy. Acceleration won't come if the electrons are revolving or moving in the discrete orbits. Now, these orbits or the shells, which he explained, were called the energy levels. And he explained that in the atom there are four shells: K shell, L, M, and N. Okay, in between was a positively charged nucleus, then was K, L, M, and the last one N. So let's understand about them in detail. So let's understand about shells. Now, there were few rules. Now shells you can't put anything anywhere. No, we shells we use for the number of electrons. How do we put it? And it is even known as electronic configuration, or electron configuration it is called. So first thing is that there is a formula that the maximum number of electrons in one shell is given by the formula 2n square. What is n? N is the orbit number or energy level, which energy level index like 1, 2, 3, and so on. So here in K shell, 2 into it, in K shell we can put only 2 electrons, L shell 8, M shell 18, and N shell 32. So here you can imagine as a restaurant, if the K floor is full, you will send it to the L floor. L floor is full, then you will send it to the M floor. So that way, this is the rule, which is the formula 2n square you have to apply over here. Similarly, there were two more rules are that the maximum number of electrons that can be accommodated in the outermost orbit will be 8 only. Outermost orbit is what? That is the n orbit. So in the n orbit, only 8 number of electrons can be placed. So, electrons are not accommodated in a given shell unless the inner shells are filled. So, firstly, you can't directly go to the n orbit. No, first you have to fill k, then l, then m, then n. Then only your shells are there, and they are filled in a stepwise manner. So, if you see over here, here is the electron configuration of few elements like nitrogen, then argon, carbon, beryllium. Here are the electronic configuration, how they are configured. So, and it is even the shells, in which shell how much electrons we will put. So, our next topic and the important topic is about valency. Now, what do we mean? Firstly, before going to valency, let's understand about the valence electrons. So, the electrons which are there in the outermost orbit, which is the n orbit, are known as the valence electrons. So here in this last orbit, here if you see, this electron is present. So that electron is the valence electron. Okay, that is the valence electron. And protons, neutrons are present in the nucleus, and only the electrons revolve in the orbits. So these are the valence electrons. Now, next is, what do we mean by valency? Valency is nothing but the capacity, the combining capacity of one atom to combine with the other atom. That is valency. Like here we say these are two atoms. For combining, this two I am taking so that they combine. So those are the four valence electrons. So here is how we calculate valency. Now, atoms, they combine to get a fully filled outermost shell with 8 electrons. Now, if this is my any element electron, okay, now the outermost shell, I am supposed to have 8 electrons in it. Okay, and 8 electrons I want, and for getting all the elements don't have a 8 electrons. So with the combining, they take from others, they give others. Okay, gaining and losing, everything happens. Then they get a fully filled 8 electrons, and 7 and 8. 8 electrons when they get, when the atom have 8 electrons in the outermost shell, it is said to possess an octet. And for obtaining a octet, there is gain as well as loss of electrons. So one will get electrons, other will give the electrons, so then only octet is found. Next is, how do we find the valency? Now, if I say valency from 1 to 4, if any element have the valency from 1 to 4, we will directly say that the number of valence electrons are 1, 2, 3. Like in lithium, the valency is 1. So, there is 1 valence electron. Similarly, in boron, the valency is 3. So, there are 3 valence electrons. So that is it. Now, if I have above 4, okay, if I have from 4 till 8, so what I'll do? I will subtract the number from 8. Okay, I'll subtract the number from 8 and I will get the valency. Like here, valency is here, it is nitrogen. Now it is above it. So what are the valence electrons? 1, 2, 3, 4, and 5. There are 5 valence electrons. So I can't say the valency is 5. No, I will subtract 8. Okay, from 5, 8 minus 5, then I'll get 3. So 3 is the valency. Similarly for neon, there are 8 valence electrons. 8 valence electrons are there, so valency is 0 here because it's already filled. So there is no valency taking place there. Alright. And any atom, if the any atom have a valence electron 7, could have valency 7 also. But it is easier to for the atom to gain 1 electron, right? Instead of using 7 of them. Right. So therefore the valency is 8 minus 1, which will become 1. So if any atom is having 7 valence electrons, so the valency will be 1. How? By 8 minus 7. So let's understand about the atomic number as well as the atomic mass of the atom. Now when I say atomic number, so let's start with that. Now we know a nucleus. In the nucleus there are neutrons as well as protons present. Okay, and the atomic number is represented by Z. Atomic number is represented by Z. So nucleus is protons plus neutrons. That will give me the nucleus, and that is nothing but the atomic number. What is atomic number? Not proton plus neutron, the number of protons in the nucleus. Okay, so the whatever number of protons are present in the nucleus, that is known as the atomic number. For example, this is an atom. Here you can see there are 4 protons, sorry, 3 protons. So the atomic number is 3 over here, and it is represented by which letter? By Z. Now, next is, for example, take that atomic number of C, which is carbon, that has is 6. So this means there are 6 protons in the nucleus. In this nucleus, there are 6 protons. Okay, and therefore the atomic number Z will also be 6 only. Now, next is atomic mass. Atomic mass is what? It is the number of protons plus neutrons. Okay, and how do we write it? We write it in the form of A x Z. What is A x Z? A is the atomic mass. X, here this X is nothing but the element. Okay, X is the element, and Z is the atomic number. So just have a look. Like for nitrogen, I write it in the form of N, 14 and 7. So what is this 14 over here? 14 is A, which is the atomic mass. So your 14 is the atomic mass and 7 is the atomic number. Alright. So, the last topic of this chapter is isotopes and isobars. So, this is the last topic of this chapter, isotopes and isobars. Now, let's understand about isotopes. So, isotopes, the atoms of the same element which have the same atomic number but different mass, they are known as isotopes. Like if I take two atoms, okay, like of the same element, but take, suppose I'm taking chlorine. Okay, one chlorine has the atomic mass as 35 and the atomic number is 17. Here also atomic number is 17, but the mass is 37. So such kind of condition is known as isotope. This means chlorine is a isotope where one has 35 the mass and one has 37. So what happens here is that element is same, atomic number is also same, but the mass is different. That is isotopes. Now example is hydrogen. Hydrogen have 3 atomic species, means they have, it has 3 isotopes, which is protium, deuterium and tritium. These are the 3 species of isotopes hydrogen has. And similarly carbon also has 3 isotopes. Now this is first one, which is also known as carbon 12 isotope. We had studied in the last in the atoms and molecules of carbon 12 isotope. This is carbon 13 isotope, and this is carbon 14 isotope. So here is the isotopes of carbon. Next is the isobars. Isobars are what? The atoms have different elements. Okay, the atoms are different. Okay, element is different. Like here I'm taking calcium and argon. Okay, but the atomic numbers are also different, but the mass number is same. For example, for calcium, the mass number is 40. Okay, even for argon also it is 40, and it is this thing atomic number is 20, here it is 80. So I'm taking different elements. Okay, I'm taking different elements, the atomic number are also different, but if the mass number, if the two mass numbers are same, then such kind of are known as isobars. They are known as isobars. For example, here as I said of calcium and argon. So there is one more term which is known as isotone. So what is isotone? Basically, the atoms which have same number of neutrons but they have different number of protons. They are called as isotones. Like two elements, they have same number of neutrons, and but the protons are different. So they are known as isotones. Like here are the two examples. Just this is a extra fact. So, thank you everyone for watching today's video. I hope it was informative, and I will be seeing in the next video where we will be discussing the NCERT solutions of the chapter Structure of Atom. Till then, stay tuned and goodbye.